Welcome to experiment number 2 for our power electronics lab, and today we are going to tackle instantaneous power, energy, and average power using Pspice. The objectives of this experiment is to simulate power electronic circuit to determine the voltages, currents, and power quantities, and to utilize the functions to measure the energy and steady state RMS current. So first, we are going to use the OrCAD capture Pspice here. The part 1 in our experiment is we will create a voltage controlled switch in Pspice. First, let's open a new project. Let's name this experiment number 2 part 1. Create a new project using analog or mix A and D, analog or digital. Then create a blank project. For the experiment, we will create the circuit as shown below. We will replicate this in the OrCAD Spice. So our source is a V-Sign supply. Let's go to place, Pspice component, search. Let's search V-Sign. So our supply is a transient sine voltage source. Double click there. Then let's place a resistor, Pspice component, resistor, there, date. You can click the ground here, 0, cap sim. Let's maximize. Then let's put a wire, let's connect. According to our diagram, the voltage amplitude of the source is 10 volts, the frequency is 60, then the voltage amplitude is 0, and the AC will be set as 0. Then let's change the value of the resistor to 5 ohms. To simulate our circuit, let's go to new simulation profile. So let's name this new simulation as EXP2 part 1. Then we will set our simulation settings to time domain transient analysis. Let's set our runtime to 16.67 milliseconds. In seconds, that is 0.01667. Click apply. Okay, let's press this play button, run Pspice. So in the simulation, we are going to test the instantaneous power, the input voltage, and the current in R1. Then let's go to trace, add trace. Let's type W, the symbol for power, then enclose parentheses, R1, then V for the input voltage. So the name of the source is V1, then we will type V1 here, plus, close parentheses, okay, there. The green one is the waveform for our instantaneous power. The red waveform is the input voltage. It's a sine signal. Then let's add the current in our resistor. So the current our resistor is, let's type I, in close parentheses, R1. So as you can see, the current in R1 started to flow in its negative cycle. So to modify this waveform wherein the current in R1 will start in its positive cycle, you just have to modify Artlet's expression. So let's put negative here. There. So with the modification, the current in R1 started in its positive cycle. Now we can also determine the average power given in the circuit. Now let's go again to trace, add trace, then so let's type AVG for average, then enclose parentheses, W, enclose parentheses again, R1, close parentheses, close parentheses. So as you can see, the code is we are averaging the instantaneous power, since the average power is the power average over a cycle or a number of cycles. There. So to measure the values of our waveforms, we can right click to any waveform, then click cursor on. Now, we can see the values here. Let's test. So let's place the cursor on the peak position of the instantaneous power. So we can observe that the waveforms in the input voltage, the current in R1, and the instantaneous power is in phase with each other. However, they have different. Now, based on the position of our cursor, we can see its peak values. For the instantaneous power, we recorded a value of 19.989 watts. For the input voltage, we recorded a value of 9.997 volts. And for the current in R1, we recorded a value of 1.9994 amperes. To measure the average power, let's click here. Then, we'll measure the value at the end of its waveform at the stop time. So the average power is 10.070 watts. To test our measured values, we can calculate the theoretical values based from the given circuit. So based from the circuit, we are given an input voltage of 10 volts and a resistor value of 5 ohms. Using the Ohm's law, we can calculate the current, which is equals to voltage divided by the resistor. So 10 volts divided by 5 ohms is equal to 2 amperes. we recorded a value of 995A, which is near to the theoretical value of 2 amperes. The measured input voltage signal in the simulation is also near or has a small difference with the theoretical value of 10 volts. We recorded a value of 9.998 volts. The formula for the instantaneous power is equals to voltage multiplied by the current. So based from the circuit, 10 volts times 2 amperes is 20 watts. And based from the simulation, we recorded an instantaneous power of 19.989 watts, which is near to 20 watts. To summarize part 1, instantaneous power is a power at a given instant, and the average power is the power average over a cycle or a number of cycles. For the part of our experiment, we will recreate the given circuit shown here. We are given an RL circuit wherein the input supply is a pulse signal or a square wave. Since our input supply is a pulse signal, let's go to place, Pspice component, search, and let's search pulse. So it is a pulse voltage source, double click, there. Since it is an RL circuit, let's place a resistor and an inductor. Maximize. Then let's put the ground, 0 cap sim. Then let's connect wires. So based on the given diagram, we will set V1 to 0, V2 is 20, TD is 0. So the TR or rise time is 1N or 1 nanosecond, and the fall time or TF is also 1 nanosecond. PW or pulse width is 8M, and PER is 20M. Let's change the value of our inductor to 10 millihenries. Our resistor 2 ohms. Now let's go to new simulation profile. EXP2 part 2 create. We will base our runtime based from this given output, 100 millisecond. So 100 millisecond is 0.1. Then click apply. Okay. Then run Pspice. So for part 2, we are going to test the current in R1 and the steady state RMS current. So let's go to trace, add trace, current in R1, IR1. So since this waveform started in its negative cycle, let's modify the trace expression to negative current in R1. Then let's add another trace. Let's type RMS, the steady state current, so in close parentheses, IR1, close parentheses. As you can see, the green waveform is the current in R1 and the steady state current is the red waveform. So in part 2, we apply square wave as an input signal to our RL circuit to analyze the transient response of the circuit. As you can see, why did we test the current in R1, wherein we can also test the current in the inductor to see how the RL circuit affected the input signal. It's because the current in R1 is also the same current that is going through in the inductor. Let's test it. Let's go to trace, add trace, then let's type in the trace expression IL1. The blue waveform is the current in the inductor. So based on the results from the simulation, in an RL circuit, the current in R1 and the current inductor is just the same. The signal of the current in R1 and the current inductor, the current is increasing to its maximum value, then it decays exponentially. In an RL circuit, the voltage across the inductor decreases with time, and the current rises to their final value exponentially. The RA waveform will be the same shape as the inductor current, since from Ohm's law we know that the current and the voltage to the resistor are related with V is equals to IR, or V is equals to current times resistor. Our circuit has the two elements, the resistor and the inductor in series, which means the same current is flowing through both components. Then we will measure the RMS current at the end of its waveform here, at the stop time. From there, we recorded an RMS current of 4.6614 amperes.